Hello again. We are going to continue Module 5, and we're going to look at the composition of compounds, like percent composition, and calculating empirical formulas using multiple different methods, like percent composition, and also like combustion analysis. I think I'm going to do combustion analysis in a separate lecture because that has a little bit more teeth to it, and it might take a little bit of time to fully explain that. So here we go. This is going to be Module 5, Lecture 2. And we are going to start where we left off before, which is the composition of compounds. Okay, let me get rid of that. All right. So in a chemical formula, in combination with the molar masses of its constituent elements, the subscript also indicates the relative quantities of each compound in a molecule. We can use the formula to calculate the percentage by mass of each element in a compound. There are a couple of ways actually to do this. First of all, I can use the formula, and a second way is actually experimentally determined mass analysis of the compound. Now, recognize that percentages may not always total 100 because of rounding. But if I want to find the mass percent of some element X, and I have the molecular formula, I can calculate the percent mass of that element X by taking the mass of the element of X in 1 mole of compound and dividing that by the total mass of 1 mole of compound. And then I'm going to multiply that by 100 because percent is parts per 100 parts. So let's look at an example. Let's look at calculating the percent carbon in 2 different hydrocarbon formulas. The first one would be CH4, and the second one would be C10H16. So if I want to calculate the mass of carbon, the percent mass of carbon in methane, which is CH4, I notice I have 1 carbon atom. So I'm going to take the mass of carbon is the mass of that 1 carbon atom. This is actually the molar mass of CH4. I'm going to take the mass of the carbon, divide it by the mass of the total, which is CH4. So how did I get that? I have 1 carbon, which is 12.011 grams, and I have 4 times 1.01 grams. This is for my carbon, that's for my hydrogen. I add that together and I get 16.04 grams per mole. That's the molar mass of CH4. So that gives me 74.88% carbon in methane. Well, what if I look at this guy? Well, now I have 10 atoms of carbon. So I have to take the mass of 1 carbon and multiply it by 10. And then I'm going to divide by the total molar mass, which has 10 carbons and 16 hydrogens. So 12.011 times 10 divided by the molar mass of that C10H16 gives me 88.16% carbon. The rest of it would be the percent hydrogen. So this is my formula. My mass percent can be calculated by taking the mass of the element in the compound divided by the mass of the compound and multiplying that by 100. So we just went over these 2 examples. There's another way I can do this. I can calculate the empirical formula based on experimental data. Remember, the empirical formula is the simplest whole number ratio of the atoms or moles of the elements in a compound, and it is not a ratio of the masses. This can be determined experimentally using a technique called elemental analysis. This can give me percent composition experimentally, or it can give me the masses of elements formed when a compound is decomposed or react together to form a different compound, which is called elemental analysis. So, how do I find an empirical formula? Let's assume I have a percent composition, and I'm going to start with 100 grams of the compound. If I already know the grams of the different percentages in my molecule, I can skip this step. Typically, I'm going to get percent composition. I'm going to assume 100 grams, because if I do that, the percent composition is actually equal to the number of grams in 100 grams of sample. Because remember, percent is parts per 100 parts. My next step is converting grams to moles using the molar mass of each element. I'm going to get a pseudo formula, because remember, the formula is really the ratio of the moles of each element that comprise the compound. I'm going to divide all of those the pseudo formula by the smallest number of moles of a particular element. If the result is within 0.1 gram or 0.1 of a whole number, I'm going to round to the whole number. This is an important part. If I'm not within 0.1 of a whole number, I might have to multiply by some factor in order to get whole numbers. So for example, if my ratio is a 0.5, to make that a whole number, I multiply by 2. So if I get 1.5 moles, I have to actually multiply that by 2 to get 3 moles, because that 3 is an integer value. So if my answer ends in 0.33 or 0.67, I multiply by 3. 0.25 or 0.75, I multiply by 4. If my ratios are already in whole numbers, which honestly happens more often than not, I just skip this step. Now, once I find the empirical formula, I can find a molecular formula, remember, which is the actual whole number multiple of the empirical formula and gives the actual ratio of the moles in the actual compound. So it's either going to be the same as the empirical formula, or I'm going to take the empirical formula and multiply it by some integer. So in order to find the molecular formula, I need to know the empirical formula. I also need to know the molar mass. So this, in many times, will be given. Then, to find the molecular formula, I'm going to multiply the empirical formula by some integer n. To figure out what this integer is, I'm going to take the molar mass of the compound. So this is the entire compound. And I'm going to divide by the empirical formula molar mass. This is going to give me some integer value. It's either 1, 2, 3, whatever. So let's do an example, because nothing is better than actually looking at how you do this in an example. And then we'll do a couple practice. So here's the problem. I have a colorless liquid. I know this liquid is 84.1% carbon and 15.9% hydrogen. So I have the percent composition. The first step is to determine the empirical formula. And then since I know the molar mass because it's given to me, I can also determine the molecular formula. Step one is determine the empirical formula. Step two is determine the molecular formula because I have the molar mass. So my strategy from before is to convert the mass percents into moles. I use the molar mass of those particular elements. And then I get mole ratios. And those mole ratios can then be transformed into the subscripts of the formula. So let's go through those steps. If I have the percent mass, I'm going to assume 100 grams of material. So if I have 84.1% carbon, if I assume 100 grams, that means I have 84.1 grams of carbon for every 100 grams of material. So this gives me the amount of carbon that I'm going to start with. So I'm going to take that value, which corresponds to the percentage, if I assume 100 grams. This is the molar mass of carbon. So in this 100 mass sample, I have 7.01 moles of carbon. I also know that the remainder is hydrogen. So I have 15.9% hydrogen. I can assume using 100 grams of that sample that now I have 15.9 grams of hydrogen. This is the molar mass of hydrogen. So that gives me 15.9 moles of hydrogen. So this is the amount. I have 7.01 moles of carbon for every 100 gram of substance. And I have 15.9 moles of hydrogen for every 100 grams of substance. I want to use these mole values in order to come up with a ratio. So basically, this is my pseudo formula. The formula in my molecular formula using the subscripts really is just a ratio of the moles in the compound. So I'm going to take the smallest value here and I'm going to divide both by that smallest value. So this, right, goes to 1, and this goes to 2.27. Well, that's not within 0.1 from a whole number. That's this one thing that I have to now multiply by 4 in that step 5 of the procedure. I'm going to scroll back up. Hope I don't give you a headache. Remember here, this is where I have, if I have the ratio that ended in 0.25, I'm going to multiply by 4. That's where I am down in this problem. So I'm going to take the values, 1 and 2.27. I'm going to multiply this by 4. So what I actually get, 1 times 4 gives me 4. 2.27 times 4 gives me 9. So this is my empirical formula. I have 4 moles of carbon to every 9 moles of hydrogen. My empirical formula is C4H9. Now, how can I find the molecular formula? Well, if I add up the masses, I have 4 times 12.011 grams, and I have 9 times 1.008 grams. What I'm going to get is 57.0 grams, which is the mass of C4H9. This is going to go on the bottom because this is going to be the mass of the empirical formula. This is the molar mass, which is given to me. So I'm going to take that and notice that the actual molar mass is 2 times larger than the mass of this empirical formula. So I need to multiply each one of those subscripts by 2, and then this is going to be the molecular formula. So this is the answer to question 1, and this is the answer to question part 2. So let's practice. For 1,000 years, the mineral chalcocite has been a highly prized source of copper. I have the percent composition of that mineral, which is 79.85% copper and 20.15% sulfur. So what is the empirical formula? Well, if I assume 100 grams, I have 79.85% copper. Actually, I just converted that to grams because I assumed, right? And I can calculate the number of moles. For every 1 mole of copper, I have, off my periodic table, I have got 63.55 grams of copper. So that's going to give me 79 79.85 divided by 63.55. That's going to give me 1.256490 moles of copper. If I do the same thing with sulfur, I have 20.15 grams of sulfur, and then for every 1 mole of sulfur, I have 32.06 grams of sulfur. So that gives me 20.15 divided by 30.06. That gives me 0.670326 moles of sulfur. So here I could write my pseudo formula. I could have copper 1.256 to sulfur. Actually, no, I have to actually divide through by the lowest number. No, actually that is true. So what I have is, I could write this formula, sulfur 0.6703, because that's the mole ratio, the moles of sulfur to the moles of copper. But what I want to do first is I want to divide through by the lowest to see if I can get this into that integer value. So I have I'm going to divide by the lowest, which is this guy. I'm going to use a different color. So I have 0.670326 divided by 0.63670326. Well, this is going to go to 1. right? And then my 1.2564 divided by my lowest number, which is the 0.6703, this goes till 1.9, which is within the values. So the formula that I get here is the empirical formula is equal to, again, if I divide this by, right, this is going to give me 1, this is going to give me 2. So I have Cu2S as my final answer. And that's how we're ending up doing these. Okay, let's do another problem. Asbestos was used for years as an insulating material in buildings until prolonged exposure to asbestos was demonstrated